The next section of Lesson 69 deals with the completely unrelated topic of equipotential lines. Let's begin with something more familiar first, namely topographical maps, sometimes called contour maps. In these side-by-side presentations of Lookout Mountain, Tennessee, you see a satellite image and a topographic map. Why do hikers use topographical maps? Because these maps, besides often showing where the improved roads and trails are, indicate elevations using contour lines. On the Tiftonia side of Lookout Mountain, you can see the bold contour lines labeled at 800 and 1200 feet. There are also medium bold contours between these numbered contours, and even lighter ones between those. These lines indicate positions of constant elevation or constant vertical height. If it were possible for you to hike along these contour lines, then you'd neither climb higher nor descend lower along your path. While most trails aren't so ideal, a hiker will know by looking at such a map where the elevation does and does not change along the trail. If the adventurer chooses a path that crosses many contour lines, then she knows she's in for a steep climb or a descent, and she ought to plan accordingly. Technically, these contour lines represent lines of constant gravitational potential, and they are perpendicular to something known mathematically as the gradient of the hill. In layman's terms, this means that the steepest part of the mountain is always perpendicular to the local equipotential lines. The hiker has only so much strength and endurance to give to the expedition, and so she'll study a topo map to learn what to expect on her hike. Now, let's translate this into electrical terms. We already know how to sketch electric field lines. These lines of electric force indicate the direction that a positive test charge would be pushed if placed in the vicinity of the charge distribution setting up the field. If we know what the electric field lines look like, then we can construct equipotential lines by making those equipotential lines everywhere perpendicular to the electric field lines, just like the contour lines of a topographic map are perpendicular to the steepest gradients of the terrain. The equipotential lines indicate lines of constant voltage, just like the contour lines on a topo map indicate lines of constant elevation. We want to know these lines of constant voltage because frequently electric charge will have to be shifted from one place to another in the region, and this shifting may or may not require energy to do it. From a practical point of view, the less energy required of me to rearrange the charge, the more energy I'll have to devote to other, perhaps more useful activities. And you as a student will be interested in such equipotential maps because they're going to appear on the AP Physics B exam. So, down here is a link to a simulation. This electric field applet allows you to put charge in various places. So I'm going to put a charge of +4 somewhere, and I'm going to show the potential gradient, the equipotential lines, the electric field lines. So now when I click anywhere in this map, it's going to put a charge of +4 somewhere. There it is. Those red circles around the +4 show the equipotential lines, and the white lines show the electric field lines. Now I'm going to put a charge of -4 somewhere. Doesn't matter where. I'm going to put it right here. And now what you see is the electric field that's mapped out, showing the standard lines of force as we've done from positive to negative charges, but the colored lines now show lines of equipotential, lines of constant electrical potential. These charges are equal in magnitude and opposite in sign, and you already know how to sketch the electric field for them. The colored lines map out the hills and the valleys, if you will, of the electrical potential. These maps can become quite complex if there are many charges involved. So for example, let me show you one. I'm going to reset this, and now I'm going to say randomize. And now I have red positives and blue negatives, and you can see I've got a very complicated map. If I randomize again, I get a different complicated map. And you can play with these and see what kinds of maps you can come up with. And these serve as contour maps. Your authors give you a couple of straightforward examples of equipotential lines. For a point charge, the equipotential lines are concentric circles, as shown in this diagram here. The circles indicate contours of equal potential or equal voltages. In this diagram, there are 10-volt and 5-volt equipotential lines that are shown. If I were to move a test charge, and you'll remember the test charges are always positive, from point A to point B, then I would cross this 10-volt equipotential line. Now, I would be moving the charge from a lower potential to a higher potential. Because the electrical force is conservative, it doesn't matter which path I follow. The work I do along the way will be the same along the paths, because it will just depend on the final point and the initial point. So I could take a path like that from A to B, or I could take a path that goes around like that from A to B. It turns out the work that I do along each of those paths is the same because the electric force is a conservative force. Somewhere along the way, I'll have to do positive work to push the test charge closer to the positive charge, capital Q, that's setting up the electric field. The work that I do on the charge is given by the equation W is equal to Q times delta V, where W is the work that I do, Q is the charge on the test charge, and delta V is the difference in potential between the points in question, in this case point B and point A. If, on the other hand, the test charge starts at C and goes to D, it's going to go downhill, and I'll be doing negative work to keep the charge capital Q from accelerating the little charge little q away from it. Finally, if I take the test charge from point B to point C, you could see that I could move along one of those equipotential lines, those contour lines, and I wouldn't have to do any work at all to shift the test charge because there's no difference in potential between point B and point C. And it doesn't matter what path I follow. I could follow any old path between B and C, and no matter which path that I follow, I'll find that the amount of work that I do along each of those paths is going to be equal to the work along any other path, because the electric force is conservative. Another common situation you'll see is between the plates of a parallel plate capacitor, as shown in this diagram. The electric field lines are uniform between the plates, which means that they don't change in magnitude or direction if I don't get too close to the edges of the plate. In this case, the equipotential lines are always sketched parallel to each other because they're all perpendicular to the electric field lines. Those electric field lines are uniform, and so this is a steady hill that goes from 100 volts down to 0 volts, and the equipotential lines are evenly spaced. On the AP exam, you'll likely get more complicated maps than the ones that I've shown for the parallel plate capacitor or for the single point charge. I'd like to show you one from this link. This link takes you to a page that has a question that is 17.4, and you'll see here question 17.4 says this: click on an answer to display an electric field plot in the right hand panel. The arrows in the field plot represent the direction and colors represent the magnitude of the electric field. Which field plot best corresponds to the potential plot on the left hand side? You can click and drag in the left hand display to measure the potential. So now if I click answer A, then what I see is I have an electric field that shows arrows pointing away down at this point, arrows pointing toward at this point, and arrows pointing toward there. Well, if I go over here and I see that I have a potential of -6 volts here, I have a potential of +9 volts here, and a potential of -4 volts here, then this charge here must be negative, this charge here must be negative, and this charge here must be positive. It looks like field A might match that. Let's go to field B and see what it looks like. Now in field B, this point here is positive, this point here is negative, but I don't see anything here, so field B is going to be out. Field C shows a negative charge here, a negative charge here, and nothing here, so field C is going to be out. Field D shows a positive charge, and a negative charge. Again, here I've got to have a positive charge, I've got to have a negative charge here, and a negative charge there. I think that field A is the right answer to this particular one. So now let's solve this problem that's in your textbook. The diagram represents equipotential lines for two negative point charges. Determine the work done by the electric field in moving a +2 Coulomb charge from, in part A, point A to infinity. B says from point A to point B, and C says from point B to point C. Let's begin with part A. First, I have a charge that I'm dealing with that's +2 coulombs. Now that's a large amount of charge, but that's the charge that your authors give you. I'm wanting to go from point A to infinity. If I look at point A down here, I see that it sits on a -15 volt contour. So the potential at point A is negative 15 volts. Now what about at infinity? Well, I have 2 point charges, and so the potential at infinity is going to be kq1 divided by r1 plus kq2 divided by r2, or you could call this q1 and you could call that q2. But if r is equal to infinity, then what that means, the potential at infinity is going to be 0, because anything over infinity is equal to 0. So I can say that V at infinity is equal to 0 volts. Now this problem asks me for the work that's done by the electric field. If we think about this, if I take a positive 2 Coulomb charge at point A, which is near two negatively charged objects, and I remove it to infinity, then what that means is I am moving away, and the force that I exert on charge Q to get it away from A to infinity is going to be essentially in the same direction as the force that I have to exert in order to move it. On the other hand, the work that's done by the field is going to be opposite that. So the work that's done by the field is going to be negative. The field is trying to exert a force in the opposite direction as the charge is moving as it goes to infinity. So I know that the work that's done by the field is going to be less than 0, because the force of the electric field is in the opposite direction of the displacement of the charge. What's the magnitude of that work? Well, the work is going to be equal to Q times delta V, where my Q is going to be the 2.0 coulombs, and the delta V is going to be the V final, 0 volts, minus the V initial, the negative 15 volts. Now I'm going to put this work in absolute values, because what I'm doing is I'm calculating the magnitude of the work. I know the sign of the work is going to be negative. So when I do this, I'm going to find that the magnitude of the work is going to be equal to 30 joules. The work that's done by the field is going to be equal to negative 30 joules. Part B. Let's go from A to B. So I'm going to start here at A and I'm going to go over to B. Well, the potential at B is this 20 volts because it's sitting on that 20 volt equipotential. I am going from a negative 15 volt to a negative 20 volt. The positive charge is moving closer to this negative charge over here, and so it is pulled closer. The field is going to do positive work. So let me calculate the work that I do. The work that I do is going to be the negative of the work that the field does. The work I do is going to be Q times delta V. Now again, my work and the field's work are going to be opposite in sign. I'm just going to figure out what the absolute value is. I'll put in the numbers, 2 coulombs times the difference in potential. The final potential is negative 20 volts. The initial potential is negative 15 volts. So I find negative 10 joules of work that I do, but the electric field is going to do positive work on this. So the work that the field does is going to be plus 10 joules. Part C. If I go from point B over here, which is at negative 20 volts, to point C over there, which is also at negative 20 volts, there is no work done because the difference in potential between those 2 points is 0. So since delta V from B to C is equal to 0, the work done by the field is also going to be 0. To recap this whole lesson, what we have done is nuclear reactions, and we have balanced nuclear reaction equations. We've also talked about work done in electric fields and talked about electrical potential, equipotential lines. The equipotential maps that you're likely to see are going to be more complicated than the ones that are given in your textbook. The idea is that you can figure out the amount of work that's done by trying to think about whether the field does work moving the charge uphill or downhill in potential, and whether the field is pushing the charge away or pulling the charge toward. That's not going to be something that you're just going to be able to have a simple formula and the formula gives you the right sign every time. You have to think about it. I'm sorry, that's just the way that it is. For now, that's it.